Hi there. Today is our last notes of the year. This is very exciting. It is one of the topics that's a little more abstract when you're first learning it. And so try to stick with me and please ask questions if you have any questions. Tomorrow we'll be doing a lab, our last lab of the year. And then on Friday we'll pull it all together. So it's very exciting. We're wrapping things up. And I wish you the best as you go through this. And again, please ask me questions if you have any. Our art of the day, the possibility cannot be displayed. Is the name of the art. And hopefully by the end of the lesson, you'll understand why I picked this particular art for our topic of entropy and free energy. So let's dive in. So entropy is a new term that you've probably not heard of before. Some of you might have. It's given the symbol capital S, which is a very strange symbol for this. And again, I really wish that I had it memorized where S comes from. I believe it comes from Greek, but anyway. Entropy is given the capital letter S. And what entropy is the measure of disorder of a system. In other words, when you have a system, how disordered is that system? Are the particles really moving fast and random, or are they very organized? If they're moving fast and very random, then that's high entropy. And if they're very organized, then that's low entropy. And so entropy has to do with order or disorder. More disorder, more entropy. So high entropy is more disorder, low entropy is more ordered. And sometimes that can be a little confusing. So try to get that locked into your head of disorder means high entropy. Order means low entropy. So if you look at these two diagrams, these are good examples of highly ordered atoms and highly disordered atoms. So highly ordered, low disorder, that is low entropy. So the left diagram shows all these atoms in a very regular repeating pattern that's very organized, and so that would be highly ordered. Over on the right, you have all these atoms that are now spread apart from one another, and so that's a lot of disorder, and that means high entropy. You can kind of think of this, if I had a whole bunch of marbles in my hand, those marbles would be very organized because they're in a nice little pile in my hand. If I throw them up into the air, they are going to go to highly disordered state. The marbles are going to spread apart. You know this intuitively. You would never expect me to throw them into the air and they all fall on the ground and pile into a nice organized pile or stack themselves into a column. That would be really weird. So if you'll think about it, is high entropy or low entropy more favored in the universe? What do you think? Well, you can think about your bedroom too. Is it more likely to be in a highly ordered state on its own or a highly disordered state on its own? Typically, you probably say highly disordered. It's easy to make a mess. It's hard to clean it up. So usually entropy, well, always entropy, high disorder is a favored state. And this idea is the foundation of the second law of thermodynamics. We learned about the first law, law of conservation of energy. The second law of thermodynamics has to do with entropy. The state of entropy of the entire universe as an isolated system, we assume that the universe, there's nothing outside of the universe, will always increase over time. Or, put another way, changes in the entropy of the universe can never be negative. So mathematically, if we wrote this as an equation, delta S, change in entropy of the universe, is always greater than zero. This is the second law of thermodynamics. Now, you may think, wait a second, I can make things more organized in the universe. For instance, I can take a whole bunch of marbles that are spread around the room and pile them into a pile. That would decrease the entropy. That would make them more organized. And you are correct. But in order to do that, you had to expend energy. You had to burn the fuel that you ate for breakfast, which undergoes cellular respiration, which produces gases, which are which have a lot of entropy. So yes, you can make things more organized, but something is going to become disorganized in the process of doing that. So overall, the entropy of the universe increased. So it's all, again, about systems and surroundings. Yes, you can make your system decrease entropy, but the surroundings is going to increase entropy in that process. The second law of thermodynamics says that entropy is always increasing. So how do you think the entropy of each state of matter compares?
Well, let's think about the states of matter, solid, liquid, and gas. Which one of those do you think has the least entropy or the most organization, the least disorder? Well, hopefully you said solid. The entropy of a solid is low. Then if we heat it up, the molecules start moving a little bit faster. They start having more randomness when they become a liquid, so that has more entropy. And then if we heat it up and the intermolecular forces break apart, or the bonds break between the ions in the solid, then we have even more entropy. So solids have the least entropy, gases have the most entropy. Solids have the least disorder, gases have the most disorder. So key examples of changes in entropy, changes in entropy. How could we increase entropy? Well, one is just like we talked about, you could melt something. If you take a solid and melt it into a liquid, you increase the entropy. Another good example of entropy increase, liquid going to a gas, vaporization. Also, if a solid goes directly to a gas, if it skips the liquid phase, sublimation, that's an increase in entropy. When you dissolve something, when you make a mixture, that is an increase in entropy. If you take a solid piece of salt and you put it in water and it dissolves, the ions break apart and now they're moving apart independently. They're not in an organized structure anymore. So making a mixture increases entropy. And last but not least, if the number of moles of gas increase in a chemical reaction, you know that you have an increase in entropy. So if you start off with 2 moles of gas in a reaction and you end up with 5 moles of gas in a reaction, that's an increase in entropy. And we'll look at an example of this in a minute. So when we talk about processes and we talk about entropy and enthalpy, we're going to be talking about the idea of spontaneous. This is an important concept in thermochemistry, is whether a reaction is spontaneous or not. And a spontaneous process is defined as one that once started continues on its own without input of energy. So like burning a fire is a spontaneous process. It takes a little energy to get it going, but once you get it going, it will continue on its own without the input of energy. That's spontaneous. Let's think about what would affect this. So temperature is going to affect it, but the two main driving forces of a spontaneous process are entropy change, and typically processes that increase entropy are spontaneous. And so increasing entropy is a favorable condition. So positive delta S is favorable. Increasing entropy is favorable. Increasing disorder. The other thing that tells us whether a process is spontaneous is enthalpy, which we talked about in the last lesson. Enthalpy is the heat change in a reaction. And so typically reactions or processes that lose energy are spontaneous. So exothermic processes favor spontaneity. So negative delta H is favorable. So you see that if these two conditions are true, a spontaneous would definitely be spontaneous. Positive delta S and a negative delta H, increased disorder, releasing energy, that would be a spontaneous process. But of course, there's a lot of combinations of these two things in processes. So determining spontaneity can't just be determined just by looking at those signs. We have to look at this mathematically. And so to do that, we're going to define something called Gibbs free energy. This is the energy that's released in a process due to the enthalpy and the entropy of the reaction. To calculate Gibbs free energy, which is called delta G, that's change in Gibbs free energy, we take the delta H value, the enthalpy change, and subtract the temperature times the change in entropy. So if you'll notice, our 3 factors of spontaneity are in here. Enthalpy change, entropy change, and then the temperature at which the reaction takes place. So delta G is called Gibbs free energy change. Delta H is the enthalpy, which is the heat change. And delta S is the entropy change, the spontaneity change. T must be in Kelvin. You have to be in Kelvin in order to determine if, in order to do this calculation. So in order for a reaction to be spontaneous, delta G allows us to figure out whether a reaction is spontaneous. If delta G is negative when we calculate this, then the process is spontaneous. If delta G is positive, then the process is not spontaneous. And again, negative means it's releasing energy. So that's why negative delta G is spontaneous. So let's look at a practice with this. So I have a reaction here. It's actually the dissolving of ammonium nitrate in water to produce ammonium ions and nitrate ions. The enthalpy change for this is 28.05 kilojoules. Notice that that's positive. So just thinking about this, this would not be a favorable condition because gaining energy is not favorable. This is an endothermic process. If you felt this when you dissolved ammonium nitrate in water, it would feel cold because it is actually absorbing energy. Delta S is positive 108.7 joules per Kelvin. So positive delta S, that is favorable. So we've got a non-favorable part of this reaction, the energy change, and we have a favorable part, the entropy change. So in order to determine if this reaction is actually spontaneous, we have to calculate delta G to see if this reaction happens spontaneously. So we're going to calculate delta G at 278 Kelvin, which is 25 degrees Celsius. Oh, I'm sorry, 5 degrees Celsius. Sorry about that. So let's go ahead and use the delta G equation and calculate delta G for this reaction. So we're going to plug delta H in, which is straight from our equation, from our information here. We're just going to plug that value in right there. We're going to take our temperature in Kelvin and plug it in for temperature. And then this one's a little tricky. Look at this. Joules compared to kilojoules. Delta S is typically in joules. Delta H is typically in kilojoules. So we're going to have to convert the delta S to kilojoules by moving the decimal over 3 places. So 0.1087 when we plug it in. So be really careful with the delta S because it must be in kilojoules in order to plug it into our equation. So now we've got all of our values into the equation. If you do the math on this on your calculator, you'll get negative 2.17 kilojoules. Notice delta G is negative. So this reaction would be spontaneous at this temperature because delta G is negative. It's releasing energy in the process. So even though the heat energy is not favorable, the entropy is very favorable, and so this reaction will occur. It will be spontaneous at this temperature. Let's take a look at what happens if we lower the temperature on this. So let's do this problem again, but this time let's change the temperature to 205 Kelvin instead of 278 Kelvin. So we're going to do the calculation just like last time. We're going to take our delta H and plug it in for delta H, same value because it's the same process. We're going to take our temperature and plug it in for the temperature in Kelvin. We're going to move the decimal over to change this to kilojoules and plug that in for delta S. And when you do this math, you end up with 5.77 kilojoules of energy. Notice this time it is positive. And since it's positive, that means overall this reaction at this temperature would gain energy, and that is not favorable. Positive delta G's is not favorable. So when we lowered the temperature, the reaction became non-favorable because all of a sudden the delta H is more important than the delta S because we lowered this value over here. So this reaction would be non-spontaneous at this lower temperature. So temperature affects the reaction. So let's just look at spontaneity and how it relates to temperature by looking at the equation. So if delta H is negative and delta S is positive, the reaction would be spontaneous at all temperatures. And let's look at why. If delta H is negative, that helps make delta G negative. If delta S is positive, subtracting a positive, that makes this side negative also. And a negative make delta G negative. So at all temperatures, this reaction would be spontaneous if delta H is negative and delta S is positive. Let's try another one. Let's say that delta H is positive and delta S is negative. So if delta H is positive, that would make delta G positive, so that contributes to making delta G positive. That's not favorable. If delta S is negative minus a negative, that would make all of this positive. So a positive and a positive makes delta G positive, and positive delta G is not favorable. So if delta H is positive and delta S is negative, the reaction would never be spontaneous. So that can't happen. Those are kind of the easy situations because it's obvious what sign delta G would be if these conditions existed. But what about if both of them were negative? If delta H was negative, that would help make delta G negative. But if delta S is negative also, minus a negative, that makes this positive. So a negative and a positive, we don't know if delta G is going to be positive or negative. It depends on, is the delta H a greater factor or is the delta S a greater factor? So in these particular conditions, delta H would be favorable. With a negative here, with a negative, delta H is favorable, but delta S is not favorable. So we need to minimize this condition. How could we minimize this condition, the delta S condition? Lower the temperature, make T very small. That would make this part of the equation smaller and increase the impact of this part of the equation. So at low temperatures, delta G would be negative if the temperature is low, when delta H is negative and delta S is negative. What about the opposite? What if delta H is positive and delta S is positive? What if instead we have a positive and a positive? So let's look at how that would affect delta G. Positive delta H, that would make delta G positive. That helps make delta G positive. That is not favorable. So a positive delta H, not favorable. But positive delta S is favorable. So we want to maximize this part of the equation. We want to make this part of the equation bigger than the first part of the equation. So how can we do that? Raise the temperature. At a high temperature, that will make the second part of the equation a bigger impact than the first part of the equation. Delta G will become more negative because of the minus sign here. So increasing the temperature will increase the entropy. Increasing entropy makes delta G more negative. So that positive and positive, you want high temperatures. I would encourage you to think about this a whole lot just to understand why this is the case, because that's what our lab is going to focus on tomorrow. So in order for an endothermic reaction to occur, there must be an increase in entropy. In other words, endothermic reactions are not favorable. Gaining heat energy is not favorable for a reaction, but the reaction can occur. Endothermic reactions do occur. So in order for an endothermic reaction to occur, you must have an increase in entropy. There must be more randomness when the reaction occurs. So that's where we're going to stop for today. You do have some practice with these concepts. I would encourage you to go through the PowerPoint on your own. I'm listing the PowerPoint just by itself in addition to this video. If you need any help with these concepts, please let me know and I'll be happy to help you out. Good luck with everything. Oh, and by the way, I hope you understand why I picked this painting for our discussion of entropy. Okay, bye.